You're there. Okay. We'll put up the Jeff will put up the link in the chat here later on. We'll let you know. You can go in there. Um, so you're talking about the virtual stuff, and I see that Dayton there's going to be a live hamvention, I guess, this year, unless something happens in between. So that'll be something to look forward to. Also, I think it's been, was it at least 3 years since I've been there, maybe 4. Excuse me. In not they still call it Dayton, but it's in Xenia, Ohio, close by. Pretty nice facility actually. That other place, the Harris Center, was just falling down. I missed the year when the sewer backed up, and so that was a good year to miss, I think. So anyway, um, I don't think I have anything else to so we'll just get into our program. We've got Marcel Stieber, AI6MS, with us here. So I'm going to turn it over to him. He's going to talk to you about batteries, and Marcel, you might give a little bio about yourself, and then the show is yours. Go ahead, and thanks for doing this.
Sounds good, Jerry. Thanks so much, and thank you very much for having me. I'm apologize. I'm on a slightly different setup than normal, so I'm on just my laptop on not on my normal QTH. So I have the chat up. So if you want to drop questions in the chat, I've got a couple of question slots too, where you can chime out in voice too. So whatever works best. But tonight's talk is everything you need to know about lithium batteries. I'll give a brief intro and jump right in. So my recommendations is keep microphones muted, but cameras on if you want. Though it's kind of small for this one, I don't have my second screen today. So comments in the chat would be great. If you want me to repeat anything, speed up, slow down. Sometimes I talk fast, so feel free to put any of those comments in the messages. I won't be offended. And definitely think of questions and especially applications or things that you'd like to work on. So a little bit of background about myself. My name is Marcel Stieber, AI6MS. I was licensed 2008 as KI6QDJ when I was a student at Cal Poly San Luis Obispo, where I did my bachelor's and master's in electrical engineering with a focus on RF and communications. So that was really my intro to ham radio was in college when I found out about amateur radio really and got licensed. So very involved still in the amateur radio club at there. And act as an advisor. I'm also part of our Cupertino Aries as a repeater trustee and RF consultant and tower climber for a bunch of other groups, local repeater groups and such. Recently became an ARRL technical specialist for my section. And in my day job, I do battery design and charging systems for consumer electronics. So there's definitely a professional aspect to it as well. Nothing here is confidential I'm talking about, of course, but there are plenty of other things that I do that I can't talk about, so that's always fun. Um, so this presentation will focus primarily on 3 different battery types. We're going to go over lead acid batteries, lithium batteries, and then talk about a particular type of lithium, the lithium iron phosphate battery that you might have heard about in the amateur radio world. And kind of talk about pros and cons about each, how you can use them and abuse them, and how to make some applications for common 12-volt systems. So we'll talk about 12-volt systems in quite some depth. This is a bidirectional QSO or conversation, so please feel free to ask questions. This talk is for you, so always happy to share what I can and go through any questions you might have. And if we need to do a deep dive, I can stick around afterwards if people want to ask particular questions about their application or something. We can always do a bigger discussion as well. Okay, so let's jump right in. So batteries, just a brief intro to batteries, because I think it's important to kind of understand some of the concepts. So fundamentally, batteries are an electrochemical energy storage system. So they're using chemistry to store electrons effectively. That's the easiest way to think of it. Typically, they're constructed in layers, and those layers allow you to have more surface area and more um, area to store these electrons effectively. Those layers are typically made of an anode, an electrolyte, and a cathode being the positive, anode being the negative terminal. And I like looking at one of these original batteries. So this battery is the made, a replica of the original 1800s battery made by Alessandro Volta. That's, yes, the Volt is named after him. And this is a zinc and copper battery. So you'll notice the layers here on the right. Oh, I forgot to adjust my mouse. That's what was supposed to be reminded. But here on the right, so you can see this battery has the different layers, and those layers are literally those anode, electrolyte, and cathode. You can see the copper layers and the zinc layers, and then in between those they have this brine-soaked paper. So that's the literally saltwater solution effectively that allowed it to conduct it. So that's an original battery looked like that. And a nice little side note too, in a schematic symbol. So this bottom image here, this is a schematic symbol of a battery, and you'll notice how those layers are also present there. Right. Technically, for a correctly drawn battery, you would match that to the number of cells that you have. So this battery here on the right is something like, I don't know, 12 or 14 cells. Um, this one here in the image would be 2 cells, right? An anode, a cathode, and another anode and another cathode. So it's kind of neat to have that. It's a fun fact next time you do a schematic and you can draw it correctly. So a couple other concepts we want to cover. One of them is a nominal cell voltage. So individual cells have nominal cell voltages depending on the specific chemicals used for that battery, right? So your typical alkaline battery is usually a carbon zinc battery, and those have a nominal cell voltage of 1.5 volts. So that's your 1.5 volt AA's, AAA's, C batteries, D batteries, you name it. Nickel cadmium, another very common one we were just talking about, that has a nominal cell voltage of 1.2 volts. Um, Lead acid battery has 2.1 volts as its nominal cell voltage. Now you go, hey Marcel, lead acid batteries are normally 12 volts. What's up with that? Well, that's the nominal cell voltage for one of those cells, right? And you have to stack multiple cells together in order to get the desired voltage. So to get a quote unquote 12 volt DC battery, you would stack a number of those bad cells together, typically 6 in the case of lead acid. Um, and in order to go for this 12 volt, we're going to focus on this mobile radio spec, which is kind of the common one that's used. If you look at your data sheets for most mobile radios and most automotive type things, they go off this 13.8 volts plus or minus 15%. And that's kind of our key design factor when we have today's presentation, is we're really focusing on that kind of 12 volt standard, which is really 11.7 to like 15.9. That's typically where those radios will operate. And that's any kind of automotive compatible system. So while we're at it, this image on the bottom right looks kind of similar. Again, you can see the layers. This is a 9 volt battery that has its case taken off. And you go, well, Marcel, there are a bunch of plates in there. I can see the carbon and zinc plates in this battery. So then I ask you, how many cells are in this? Um, and I don't know, we can't do show of hands here, but if we look at the number of cells and you count it up carefully, you'll see that you get 6 sets of cells. And since it's a nominal cell voltage of 1.5 volts, that's 6 times 1.5, which is 9 volts for your 9 volt battery, right? So the science works. Slight disclaimer, some 9 volt batteries actually are built with 6 quadruple A batteries in there, but they're still in series, so the same thing applies. But that should give you an idea of what that looks like. Okay, so first battery chemistry, lead acid. I'm gonna try to not spend a huge amount of time here, but I think it's good to have the background. Lead acid batteries came around in about 1859, and they're typically, for a 12 volt construction, there's 6 sets of plates or 6 cells that are soaked in electrolyte. So they use pure lead on one and lead oxide on the other side, and then sulfuric acid. That's that nasty acid that people always are worried about spilling for the lead acid batteries. So this image here on the left, that's a cross section of a motorcycle battery. And you can see the 6 chambers, right, that are then all connected in series to get up to your 12 volts. And on the right here, that's again a kind of a cross section of, or a cutaway from a automotive battery. And you can see again those sets of plates in each cell. So again, 6 cells in series with the plates in each to increase the ampacity of that battery, or the capacity of the battery. For lead acid, that 2.1 volt nominal is that nominal voltage of that cell for the chemistry. And when you look at the typical range of that, it can be anywhere from 1.3 up to 2.45, right? So that's the minimum charge all the way up to the maximum charge. And again, that varies a little bit. Within lead acid batteries, there are different types and varieties. So those will change a little bit. But if we look at the nominal voltage for 6 cells, that's around 12.6 volts nominal. And then at the low end, it'd be down at 10.8, and the high end would be about 14.2, which some people know as kind of the car's alternator voltage, right? And that's why the car helps charge that battery, right? It's all coming from the automotive world. This table here is a little bit complex, but I'll briefly address it because I think it's kind of important. This is a capacity versus so it's a runtime versus current draw. So current draw here is given in what's known as a C rate, or a capacity rate. So if it's a 10 amp hour battery and you're pulling a 1C charge from it, that's pulling 10 amps from a 10 amp hour battery. And this should last in theory for 1 hour, right? If it's 10 amp hours. Realistically though, for lead acid, you're only pulling about 25 minutes or so before it's dead, right? So that's less than half of the expected capacity. In order to actually get higher rating, you'd be running it like, or the higher capacity is like 0.1 C, so that's a tenth of a C. So for a 10 amp hour battery, a 1/10 C charge rate would be 1 amp of continuous discharge. So 1 amp of discharge, you can get almost 10 hours of capacity out of this, out of runtime. So 10 hours out of a 10 amp hour battery is only capable for 1 amp of discharge, right? So lead acid batteries, you don't want to discharge them at what the rate is. You have a 100 amp hour battery, lead acid battery, you don't want to pull 100 amps from it. It won't be able to do that for very long, right? So this is important because when we actually talk about run times for lead acid batteries, we usually can only get about half the rated capacity out of them when we're talking about typical applications, especially when you're transmitting on a radio. Looking at this as well, so if we put that 13.8 volt line on here, um, you can see that this lower line, that 11.7 volts, is pretty high up here on this chart, right? So anytime any of these lines drops below that, you're going to lose that radio. The radio is no longer going to be able to operate there. So that's a struggle. So a couple different types. So sealed lead acid is kind of the big one of the big categories, or SLA, and that has several subcategories, including absorbed glass mat and gel cells and deep cycle variants. I won't go into depth on those. They have different purposes. Cars are typically are often AGM. Deep cycle variants are more like the marine type ones that you see for trawling motors and that sort of thing. Flooded cells are ones like this one here on the bottom right. This is a 200 amp hour system that's flooded cell. So it's liquid electrolyte, and they have to sit upright and they have to be vented for outgassing. They last a lot longer. These can last for 10, 20 years, but they need to be cared for and fed and maintained and watered, quite literally. It's also interesting, this one here on the right, you can see there are, again, 6 cells in series here, right? So even though this is a large battery bank, each of these is a one single nominal cell of 2.1 volts across those terminals. And then with 6 of them in series, you get your 12-volt system. So pros and cons. So lead acid batteries, they're very sensitive to deep discharge. So if you discharge them all the way to zero, um, you're going to damage the capacity quite significantly, which means, kind of like we mentioned in the previous slides, you don't get the full rated capacity. So typically, you run them down to like maybe 50% depth of discharge, and that means only discharging them halfway. And if you discharge those batteries halfway, you'll get maybe 500 cycles out of them. So for like a solar system, an off-grid solar application, lead acid batteries might only last you 500 cycles if you're doing a full cycle every day, or a 50% cycle every day. That might only be 1.5 years, right, before those batteries are end of life, right? So they don't last very long from that perspective. They're also super heavy. They have the word lead in them, so that chemistry is heavier. And they only, for sealed lead acid batteries, they typically only have a 5-year shelf life. And this one's actually kind of funny because if you go to your local Home Depot or somewhere and you're ordering a battery, you're buying a battery, check the date code when you purchase it. Make sure that it's something that was manufactured recently. If you end up buying a battery that's already been sitting on the shelf for 3 years, you only have 2 years of manufacturer data sheet shelf life left. So you're only paying for 40% of the battery that you're getting, or you're only getting 40% of the battery that you're paying for. So ask for a discount. Let me know how it goes, because that should be good. I did actually, recently get lead acid. That was manufactured only 3 years prior, or 3 months prior to when I got it. So that's good. But I also have had a case where I went into Home Depot to pick up a little replacement battery for a UPS, and that battery had been sitting there for 2.5 years, I think. And no, they did not give me a 50% discount. So I tried. But lead acids are super available currently, and you can get them all over the place pretty easily. Um, with this caveat that total cost of ownership can be higher due to replacements. So if you're using these in an off-grid application or where you're cycling them heavily, you'll need to replace them quite often. And if you're getting sealed lead acids, they only last 5 years, so you have to plan to replace these every 5 years. They might last you longer. They might not last quite as long depending on your usage, but plan for that. So really think of it as a 5-year depreciation and amortize that accordingly. Briefly, lead acids are super capable. I'm probably going to skip this slide, but high level, it's super compatible because all of automotive runs on 12-volt lead acid, right? So there are chargers everywhere, there are testers everywhere, there are tons of battery boxes and everything available, and a lot of the existing kind of amateur radio systems are designed to work with those directly. So something like the West Mountain Radio Super Power Gate, I stole this from their website. They have this really simple system where you just plug in the battery to a port and it automatically charges it and then does a battery backup. One note that I add to this slide here, this UVLO, or under voltage lockout, That's not something they include by default, and this is actually a big mistake. So these lead acid batteries, like we mentioned, really don't like getting discharged fully. It can literally kill them. So like your car, if you ever left your car lights on and it discharged all the way to zero, newer vehicles have a cutoff, but older vehicles, you could drain it to zero and that battery is dead. There's no recovering that. Even after a jump start, you might be able to make it around the block, but it won't be the same ever after that. So you want to include some sort of under voltage protection here. So they sell a PowerGate Plus, which is an extra 115 bucks, or you can get these little modules off eBay, which are a relay with a little voltage sense that you can adjust the threshold and have it just disconnect the battery from the load so you don't over discharge it. So that's lead acid. Wanted to give a pause here for any questions on lead batteries. This is a picture of a 100 amp hour, what is it? I think 100, yeah, 108 amp hour battery in a box with the little power supply in that power gate, and the UVLO is buried there as well. This tips out the scale at just shy of 75 pounds, right? So most of us are not comfortable lifting 75 pounds like that. So if you need that much power for a field day deployment, it might be tricky. So lead is heavy. Okay, seeing no questions, we'll roll right along. So next section, lithium ion. So lithium-ion batteries came around quite a ways later. So 1970s is when these really started. They typically involve a jelly roll construction. Again, it's layers, right? But instead of the layers being stacked on top of each other, you're rolling them up. That's most lithiums are built like this. There are other styles too where they still stack them up. But I'm focused mostly here on the jelly roll construction as they talk about it. Or pouch cells are also typically built like this in your cell phones and tablets and laptops and stuff. So similar to an electrolytic capacitor, that's the best analogy that I have. Similar construction where you have an anode, a cathode, and the electrolyte, but then you also have a separator. Since it's rolled around on itself, you have to make sure it doesn't short between those layers that you don't want to actually communicate or like have electrons flowing between. So you have an insulator layer that's in there to prevent that. Because of this construction and the chemistry, you can have a much higher specific energy versus lead acid. So um, lead acid's only around 140 kilojoules per kilogram, whereas lithium ion chemistries are somewhere in the 400 or 500 range for that. So four times the capacity effectively. Specific energy, which is kilojoules per kilogram. So it's using weight as the denominator here. The nominal cell voltage for lithium ion chemistry is usually around 3.6 volts. There are different chemistries which have slightly different nominal voltages. So like lithium polymer is typically 3.7 nominal, but it kind of depends on the specific chemistry again. The range of these cells is somewhere from like 3 to 4.2 volts. So if we think back to the lead acid where the nominal was 2.1, right? And it was going from 1 point something to 2 point something. This goes from 3 to 4 something volts, right? So it's a much higher voltage overall. There are a ton of different chemistries that are suited for different applications. They use lovely three-letter acronyms. So LCO, NMC, LMO, LFP are just a couple of them. So that's lithium, cobalt oxide, nickel, manganese, cadmium. I'll give you an idea, right? Lithium ferrophosphate, that's LFP, the last one. So these are just different chemistries that are suited for different applications. Sometimes they're for high energy. Sometimes they're for a high current or high power handling capabilities. So for a power tool, for example, you want it to have a really high amperage or ampacity that it can push out a lot of amps at once. For a power bank or for a cell phone, you might want it to be able to last very long, so have a higher energy density, have more energy in it as an energy cell, and not necessarily as much pulse current. Form factors, the two main ones I'm talking about are pouch cells. That's the one here on the bottom left. And that's that jelly roll is taken and flattened and then put inside a pouch and sealed up so that no air gets out or no air gets in and no electrolyte gets out. Or they're in these cylindrical cell formats. So that's many of you might have seen these typically. So these are little 18650 or 21700. That's the size of the cell, so 18 millimeters diameter and 665 millimeters long, right? 21700s will be a little bit wider and longer. And these are typically found, older laptops have them, electric vehicles have them, and power tools, very common. So most of the Ryobi's, DeWalt and stuff use those. Though DeWalt just announced that they have a new pouch cell battery that they just released this year. So times are changing, which is why I added the laptops, EVs, and tools to both categories, because it really depends on the application, what people end up using. So lithium ion. So really key things here is that they're highly, highly sensitive to over voltage and over current events. that can lead to thermal runaway or spontaneous decombustion or rapid disassembly, or choose whichever nice word you want besides fire and explosion. The battery industry generally tries to avoid those. So in order to protect against these, you need to have protection circuits built in, right? So your battery chargers need quite literally millivolt accuracy when you're charging these cells full. Because if you overcharge by sometimes as little as 50 millivolts or 100 millivolts, you can lead to one of these over voltage situations. So multi-cell packs need a battery management system or a BMS of some form. And at a very bare minimum, you need over voltage protection, over current protection, and over temperature protection. And again, lots of abbreviations here, right? Um, and the key thing, those are really the critical ones, because those are the ones that will cause your battery to go boom. Ideally, you'd have a couple additional protections, including UVLO again, so under voltage lockout or low voltage protection, cell balancing, which makes sure all the cells stay at the same voltage levels. And then you probably want some features like fuel gauging to actually tell you what percentage battery capacity, like your cell phone or tablet would tell you, or laptop would tell you what percentage battery you have. Um, the image here on the bottom left, this is a typical BMS kind of drawing for a 4-cell pack. So you can see here with 4 cells in series. So again, we're building up a higher voltage battery pack with 4 cells in series. You have a voltage tap in between each set of cells. So this battery management system now has a high accuracy voltmeter effectively sitting across each of these cells, right? And it's very accurately measuring the specific voltage across that one cell. And if that ever gets too high and it hits an overvoltage condition, it can open up and flag an error. It'll open up the charger discharge FETs. It can protect the battery pack when that happens. It can blow a fuse depending on the pack. They've got different ways to protect themselves. So that's typical. That's basically how they work, right? They're literally measuring every single cell voltage to make sure that you don't exceed these scenarios. They'll also have a sense resistor in them for current over current measurement, and then they'll have some thermistors on them. Sometimes thermistors on the cells as well, to make sure that no cells get too hot, that they might get, again, thermal runaway. So that's the high level critical factors about lithium chemistries. Good and bad. So there's a challenge with voltage range mismatch, and we'll get a deep dive into this for how to get it to work for these 13.8 volt radios. But they're really good for non-standard, non-standard, I put in quotes as well, radios with better input voltage ranges. So things like an HT, they're typically running on either 1 cell or 2 cells directly. So like an HT, if it's running off 5 volts, they might give it 2 cells in series, which will give you kind of a 7.2 volt nominal cell voltage, or 7.4 for lithium polymers. So if you take off your HT battery pack and look at the inside, you'll often see it's a 7.2 or 7.4 volt battery. And they can easily step that down to 5 volts to run the microcontrollers on there, or the power amplifiers, or they run it directly into, depends on the capabilities. Um, the cons for these batteries: high cell voltages are hazardous, right? We talked about that. So very dangerous. If you overcharge these, that's a really easy way to do some pyrotechnic demonstrations. Do not recommend. Cycle life really varies, and this depends largely on the cells and the specific application. So this image on the bottom right is kind of a typical discharge curve for cycle life. So on the x-axis, you have the number of cycles, and on the y-axis, you have the capacity. So this one started in nominal capacity around 2,600 milliamp hours, and after, what is that, 300 cycles, you're down at 2,100 milliamp hours, right? So that's always a little bit tricky for how much capacity is left. But this depends on the test conditions and how you're using it. So typical lithium chemistries, 300 to 500 cycles gets you to about 70% capacity. So if you think about that for your cell phone, that's kind of 1 to 2 years of usage, depending on if it's discharging a full cycle every day. You might only be doing a half cycle a day, depending on how you use your pack or your phone. And after 1 or 2 years, your battery might be pretty degraded already, so you might only have 70% of the capacity left. On the benefit side, you do have high energy density. You do have some issues charging below 0 degrees C. So I added this specifically for the Denver group here, since you're often in colder temperatures. Lithium batteries do need some extra care and feeding if you're getting below 0. So they have batteries with built-in heaters in them and stuff to keep them above 0 when you're charging them. Many of the chemistries can be discharged below 0, but when you start charging, you need to make sure they're above 0. And some packs have like built-in heaters, and they'll automatically do this. So if you have like an off-grid solar system, in the morning when the sun comes up and it wants to start charging the batteries, if the batteries got to less than 0 degrees C, they'll put that energy from the solar panels into the heaters first to bring the batteries up to temperature, and then it'll take the energy and put it into charging them once it gets them to a certain temperature. Benefits, super low cost, and they are everywhere. So lithium ion batteries are really, really, really available. Though they're also in high demand, right? Electric vehicles are all over the place and picking up.
I got a question.
Yeah, please.
Uh, how cold, at what low temperature will a lithium ion battery stop working?
Loaded question. So the chemistry itself will literally move more slowly at lower temperatures. Different batteries, depending on the pack integration. So again, the battery management system that's in here, it'll often have disconnects built in. So most packs that you get that have an actual protection circuit in them will self-protect. So if you get below 0 degrees, it will turn off the charging capability until it gets above 0 degrees. So like literally you have to like warm it up on your, under your sleeve first before you can start charging it. That's kind of the short answer. It kind of depends, and different chemistries will also behave a little bit more differently. So yeah, did that answer your question, Bill?
Not exactly. I mean, I run recording equipment, or where I work, we run recording equipment as far north as Barrow, Alaska. And a year or so ago, we had the heat in the building fail. And we were just running it on lead acid car batteries, and everything stopped working about when the temperature inside got to about 30 below because there was no heat. And how would a lithium ion battery last about that long, or could it withstand colder temperatures before it freezes up and stops?
Yeah, I think we might be maybe deep dive that after the presentation. Short
Okay.
version, so like the lead acid batteries at those lower temperatures likely had increased resistance as well. So you have more voltage drop as a result. So that could have led to a premature brownout situation effectively. Um,
Mm-hmm.
and lithium batteries, there are chemistries that are designed to work at lower temperatures like that, or some of them will have built-in heaters even during discharge so they can keep the battery warm and still let you get some extra capacity out of them, even though you're now burning more heat to also keep them warm, right? Or burning energy to keep them warm. So there's a trade-off there. Um, but yeah, maybe let's chat a little bit more afterwards. I think because
Okay.
it's the extreme scenarios get a little bit more complicated, and there's definitely some prior art. So the folks down in Antarctica as well, and a number of other ones in Canada, they have a lot of off-grid systems that they're running, purely solar powered, where they keep the batteries in coolers with heating elements in them to actually keep them warm, right? Like in insulated igloos. So that can definitely be something that you can do to help those scenarios as well.
Okay.
Cool. Any other questions while we're there? Okay. So a brief integration here. I'm going to skip over a little bit of this just from I think what's interesting for folks, but I think from an integration perspective, when we talk about battery packs, especially lithium ones, we typically talk about series and parallel strings. So there's this terminology of like 4s1p or 7s10p. So that's the number of cells in series and the number of cells in parallel. So when you're building up these battery banks, and like if you've heard of Bioenno and stuff, they're doing the same thing. They have cylindrical cells inside and they're stacking them up. If you stack them in series, you increase the voltage. And if you stack them in parallel, you're increasing the capacity, right? Basic Ohm's law here for how that works out. So this image on the left here, that's in theory, this is a 1 series and 3 parallel based on how the image is. So the ends of them are all connected together, and then there are 3 packs in parallel. The one on the right would be 3 in series and 2 in parallel. So you get 3 times the voltage, but twice the capacity of an individual cell for that total pack, right? And that's kind of how these are built to get to different voltages. So when we look at these voltages and we start with that lithium system, you can see that you're going to struggle to get it within this 13.8 volts plus or minus 15. So for your typical 12 volt system, with a 3S pack, your nominal is already too low. You're at 10.8 volts nominal, so you're not going to be able to power your radios even when it's just normally sitting there. Fully charged, you'll be able to get it for a little bit, but you really need a boost converter or something to get the voltage up. With a 4S pack for regular lithium chemistries, nominally you'll be good at 14.4, but at the upper end, you're actually too high. So 16.8 fully charge a 4S lithium ion battery pack. So like an RC plane, I've seen people do this. They put power poles on it and try to run their radio on it. If they fully charge it and plug in their radio that can't handle 16.8 volts, you just blew up that radio. That can be an expensive HF radio mistake. So for these, you typically need some buck or boost converters to manage that. But the other thing you can do is you just don't charge them as full. So if you know, and you do this with caution, but if, for example, your radio can handle 15.87 volts exactly, and that's what the data sheet says, you could charge your battery pack to 15.87 volts, so about 3.95 volts per cell, and you'll just lose a little bit of capacity. So your total pack might be 10 or 20% lower capacity, but you don't have any buck or boost converter. So there's a little trade-off there. Or you can go with higher series packs. So with greater than 5S, you're going to be above those limits pretty much. So you need some sort of buck converter to get you down. Problem with converters, of course, is noise and efficiency. So HF noise is pretty common. You can get more expensive ones that are better filtered and don't have those issues. But they also have some sort of efficiency. So you can get mid 90% efficiency at certain loads, but in other cases, it could drop significantly lower than that. So there's a little table here, just I'll briefly flash this. So for a mobile radio, this is the range, the voltage range here on the left that you're trying to go 11.7 to 15.9. Lead acid batteries are kind of on the lower end here and they drop off pretty quickly. A 3S lithium pack is too low, 4S kind of in the middle, okay, maybe, and 5S too high, right? Just to kind of visualize how that maps with that mobile radio range that we're trying to align with. So when we put this together, this is one that I built up, which was a larger battery pack using a whole bunch of cells. So it's a 7S10P, so that's 70 cells in this battery pack. It's from the DIY Powerwall community online. They build their own like power walls to power their house in power outages. In this case, I used it to build a little kind of 24-volt pack that has a buck converter on it. So pretty straightforward. You have a battery pack on the left here with its own battery management system. Again, you always need that battery management system. And then the only other key factor here is this DC-DC converter. So that gets me from the input voltage of the battery pack to a steady regulated 13.8 volts out. So right on the voltage that I want, we output it. And then we have all the other things, battery disconnects, a voltage and current monitor for me to see the capacity, a charge port, some power pull outputs, some USB outputs, because why not? You're building a nice battery pack, right? It's quite expensive to build one of these by hand, especially if you're buying the cells. The cells can be $5 each. This price is a little bit out of date, and there are newer versions of these cells now too. But a total pack like this is around $600 if you're buying it all off the shelf. So a lot of people will salvage their parts. So the DIY Powerwall community, they're usually taking apart old laptop batteries and testing them and then individually using them. There's a whole resale market online of people that just test old batteries and resell them. There's a whole circular economy there, which is quite cool. So mine were also salvaged when I built it, so I saved my $350 significantly. So this is what that battery pack looks like on the inside. Top left, you can see each of these black rows has 7 cells in it, and then there are 10 of those stacked together with the battery management board in the middle, and then big red switches and blinky lights because that's what we like as hams, right? So always fun. So the tests, I ran some tests on this because again, we have a buck converter in here and we kind of wanted to understand the efficiency, right? So at a low output current, so this is a 30 amp buck converter, so it's relatively capable. So I designed that intentionally so I could run like an HF radio or 2 radios on it for a net control station, for example. But at a low output current, when the radios are just on standby, we're only getting like 87% efficiency. So pretty low efficiency. We're losing 15%. Bill, do you mind going on mute over there, or I can mute you, maybe? There we go, mute. Okay, cool. I guess that worked. So yeah, 87% efficiency. At higher output currents, the efficiency goes up. So as we get closer to that 30 amps that the converter is rated for, we're getting 92 to 96% efficiency. So that's actually quite good. But again, you're not usually going to be pulling that high of a rate. So designing it so that you have the efficiency at the points where you're typically using it will get you the best bang for your buck out of that battery pack. So that's pretty key. This is a fun one. So I have a West Mountain Radio CBA4. That's their computerized battery analyzer. It's a great tool for measuring batteries or solar panels, even, and all sorts of stuff. So when we calculated the pack, we calculated 590 watt hours by using the cells and doing some math, and we measured 608 watt hours, which was great. This was assuming 90% efficiency because we did a 5 amp steady state discharge. And this is a really funny discharge curve. For people that are used to seeing battery discharge curves, you'll see one later. This is hilarious because it's just a flat rectangle, right? It's just flat, perfect 13.8 volts regulated output from the buck converter. And then when the low voltage cutoff in the battery management system kicked in, it dropped to 0, right? So battery nerds laugh at this sort of graph because it's quite amusing. But it gave us a good data point here, and the theory lined up quite nicely. So that was good when we saw that. So this ran, to give you an idea, this battery pack pulling 5 amps, which is about 70 watts of discharge power, ran for just shy of 9 hours, right? So that would be quite a bit of power handling in this suitcase. Cool. Any other questions at this point? And get to the fun part now. Okay. So last part here is lithium iron phosphate. A couple different abbreviations. You might have seen LiFePO for, that's some people, or LFP for lithium ferrophosphate, right? Because Fe is for iron. Whatever you like using, I've gotten used to LFP at this point because it rolls off the tongue a little bit better than LiFePO for, but whatever works for you. So this came around in around 1996. So quite a bit later, right? 1970 was when those lithium ion chemistries first came out. And then 25 years later, 26 years later, they came out with this specific chemistry, right? So same general jelly roll construction is what you typically see, but it's a different nominal voltage for this. The nominal cell voltage is 3.2 volts, right? So compared to that 3.6 volts nominal for regular lithium chemistries, lithium iron phosphate is down at 3.2 volts nominal. So this is great, right? The voltage range goes from 2.5 to 3.65 when you're fully discharged or fully charged, roughly. Again, it varies a little bit based on the specific chemistries. But that means that a 4S pack, so if we take 4 of these in series, we're getting a nice voltage range here from 10 to 14.6, which fits pretty nicely in that chart here, right? So if we look at this chart, we can see that sits quite well here compared to the mobile radio land, because it brought this lithium ion 4S, which was a little bit high, and now brought it to the a little bit low, right? There's about 5% capacity that you lose at the lower end here as it drops off below the 11.7 cutoff for most mobile radios. But that usually works out okay. So this is why it's so desirable. This is why you've seen it take over the amateur radio world. The cost has come down because it's about 20 years since it came out, and then it really, or was it? Can't do that math. 15 years since it came out now, and the cost really dropped down since then. So, sorry, 25 years now. I can do math. Don't worry, folks. So lithium iron phosphate, the really cool thing is they're super available as 12-volt battery replacements. Because they line up so nicely to this, you can literally drop them into a lot of existing systems that were designed for lead acid and put in a lithium iron phosphate battery just as is, just put it in and it'll work, which is pretty amazing. So you can get automotive and motorcycle battery replacements for your car that are lithium based. Now, based in Denver or based up north where it's cold, I don't necessarily recommend it because again, at colder temperatures, they won't perform as well. But they could be a nice drop-in replacement. They're way lighter, so a lot of race vehicles will actually use these because they're so light. They come built in with all these protections already. So when you buy these as battery packs, so like this image here on the bottom left is actually a Bioenno battery pack. I met them at a conference and they had one of them without the heat shrink, the blue heat shrink on it. And you can see this red circuit board, that's the actual battery protection module that has the battery management system on it. So this has over voltage protection, over temperature protection, under voltage, over current balancing. All of those things are built into this, which is great, right? So you can hook them up directly to your radio, no DC to DC converter. You'll even notice this battery on the bottom right has a power pole directly on it. So if you've chopped off the leads on the back of your radio and hooked up power poles on it, then you can literally plug this directly in. It'll be perfectly fine. The battery management system has effectively an electric fuse in it as well. That over current protection, right, is a fuse effectively. So you don't necessarily even need an additional fuse in the system, though most people do. So that's really great about these. So a couple pros and cons. So number one, they're intrinsically safer than other lithium-ion chemistries. The electrolyte's different, the chemistry is different. They just aren't as dangerous. They're much less likely to go boom. Right? They still can get damaged by overvoltage, but you have to overvoltage them more. So not just like 50 millivolts over for some chemistries, but these you really have to push a little bit higher before they get dangerous. Um, Higher cycle life. This is a really key one, especially for the solar and off-grid community. You can get thousands of cycles out of these packs versus just hundreds for regular lithium-ion chemistries. So again, it depends on the specific conditions, but there are packs that can get 2, 3, 4, 5,000 easily. And there are even lithium-ion phosphate packs that go up to 10, 15, 20,000 cycles, depending on their cycle life conditions. So that's awesome. They also have lower self-discharge and better aging. So that means that just sitting on the shelf, they're less likely, they don't lose as much like energy over time as regular lithium ion batteries do. Like if you just take your cell phone and turn it off or your tablet and turn it off and leave it on the shelf for a couple months, it will have dropped, 5, 10, 15% capacity. lithium iron phosphate can run 6 months to a year sometimes and only drop a few percent. Now, downsides, of course, there have to be some downsides. So one is lower energy density. So they're not quite as energy dense for kilojoules per kilogram again, right? So 360 versus 460 for regular lithium ion. So it's about 25% or so less capacity. And they're more expensive. Though these numbers change really rapidly and really depend on a whole bunch of factors. There are a number of low-cost ones that just in the last 12, 18 months, there are a whole bunch more vendors in this market, and this market is rapidly evolving. So while on paper, if you go online and just look up some numbers, like a 20 amp hour lithium iron phosphate battery from Bioenno is around $200, and a lithium ion battery pack of kind of similar capacity would be maybe $120. And a lead acid might be significantly less than that. But keep in mind that a 20 amp hour lead acid battery is not really a 20 amp hour lead acid battery. It's only about half that, right? So if you can only have half of that as usable capacity, then really you need two of those. So that's $60 to $120. And at that point, you can see you're getting pretty close to these prices, right? And if that one's only has a shelf life of 5 years and you have to replace it in 5 years, if you're planning on keeping this for more than 5 years, there's really no reason not to buy a lithium iron phosphate battery pack at this point. And they keep getting cheaper. So highly recommend. So 2 ways you can get into this fun party and get some batteries. The first one is you can buy a pack or you can build a pack. So we'll start with buy a pack. So Bioenno is one that in the amateur radio community has become very, very popular. They got into that market pretty early and made it themselves a very good name. I've met their designers and CEO, I think, at a conference several times. They come out to PacificCon and some other places, and they really do know their stuff. So they build packs well. They have the right protections built in. They have chargers that you can buy with their batteries. They're great. They're just work. They have nice little lights on them. And they have a lot of good information on their website as well. I'm not paid by them. I've never been given anything by Bioenno, but I honestly do think that they're a good company and they do make good products. So if you're looking for just a simple answer, Marcel, what should I go buy? I want to power my HF radio in the field. I want to go power my QRP radio in the field. I would say probably just go with Bioenno. It's safe. They've been in the market for a long time, and they make some great options that a lot of hams use. If you want, you can put it in a nice case like I did. So add a hard case, add some ports and some USB outputs, and then you can make a nice little box like this. So this is just a little Pelican case that I had lying around. Finally got a good project use for it. Wired it up, and the battery hooks up to it. Just has some jumpers to the outside to make some nice panel mounts. Has a little voltage meter on it, and then some USB ports so I can charge some phones and stuff off of it. Pro tip, always keep USB cables in these boxes. So I always have, a micro USB, a USB-C, and a lightning cable in each of these boxes, so that whoever needs a charge will have the cable there. Because otherwise you're like, well, I have this great battery and your phone's empty, but we have no way to hook the two together, right? So always keep those cables around, buy them in bulk and keep them everywhere. That's my pro tip. The other thing you'll notice is I put this label on my battery. So label makers are my friend, and I put all the statistics on here because I think it's really helpful. If you're in the field, you won't necessarily have an internet connection to go pull up the PDF data sheet, assuming that the websites and the internets are all up and everything, that you can actually pull up the data sheet for this pack. So I write these numbers down: the battery pack weight, the charge voltage, the charge current, the voltage range of the pack, and the max continuous discharge and the max pulse discharge. So this has a 40 amp max continuous discharge and a 60 amp 2-second pulse, right? These factors are key because I'm going to go field charge this or use this in the field and I'm trying to debug something. Those are key numbers for me to know if I'm going to exceed the capabilities of the system that I'm using. So I always recommend that. This is what a typical discharge curve looks like. So you see it starts up pretty high, but most of the time it's sitting here between 12 and a half, 13 volts is where it sits pretty flat for most of the discharge curve. And the very end is called the hockey stick curve, where it kind of drops off. So again, that 11.7 point is pretty far down here on the hockey stick. So you're only losing this last couple minutes of runtime when it drops below that, but the rest of the time is pretty good. One other sign of a good manufacturer, this battery pack is specified for 220 watt hours, and I measured 254 watt hours. So that's great, right? They're not overselling their product. They're selling it at a nominal or minimum rated capacity. They guarantee that it has 220 watt hours, and it comes in nicely above that. That means usually good grade A cells that are coming fresh from the factory and haven't been abused or reused or damaged or anything. So that's key. The other thing you can do is build your own pack. This one I built a few years ago using prismatic cells, so they're slightly different construction, but same lithium iron phosphate battery chemistry. You add a battery management system. So I picked a fancy Bluetooth one. That was one of the more expensive ones that you can get, like 70, 80 bucks. A nice case. This one was given to me. So this PowerWorks battery case, bright orange, which I love, and has all the plugs and ports on it and everything. And then I just bought a Bioenno charger because I honestly think they're quite good and just work. So it's a kind of a set and forget charger to just use in there. Building it yourself, and these prices again are a couple of years old at this point, but the battery by itself, not counting the box, is about 291 bucks, like let's say 300 bucks, versus the equivalent 50 amp hour Bioenno battery off the shelf is 450, 470 bucks. So you can definitely save a chunk of change if you build it yourself, if you're so inclined and you have the right safety mechanisms to do so. Now, building your own pack means that it's going to look something like that on the top right with zip ties and electrical tape holding things together. Probably, unless you spend the time to go even beyond that. So keep that in mind, and definitely encourage people to build it. If you're building a bigger battery bank, that can definitely save you a lot of costs. If you're doing a battery backup for your shack, for example, and you want 100 or a couple hundred amp hours of capacity, those have come way down in price these days, and that's definitely cost effective to build one yourself, and it's pretty straightforward too. This is what that battery pack looks like. You can see there's actually quite a bit of space in this box. The box is actually designed for a 70 amp hour battery, and I'm only putting a 50 amp hour in there. But again, my little zipper pouch with USB cables and the charger, everything in the box ready to go. So that is my power system. I can go anywhere. I can charge it from DC, I can charge it from AC, and it can provide DC. I sometimes also drop my little inverter in there, and then I can provide AC as well, right? So it's just a Go box for power. And yes, on my other Go box that has my HF radio in it, it says on the top, don't forget power and antenna. So I grab the orange box, I grab the black box with my HF radio, and then I grab the tube with the antenna in it and go, right? So make sure you have all the pieces you need. This one is a smart BMS. I love this as a battery nerd. You have Bluetooth control over the actual battery stats, so I can go in and change all these settings: the over voltage, under voltage, over current, under voltage, over current, temperature settings, everything you can configure, which I absolutely love. You can also break stuff very easily, so right, your mileage may vary. You can get non-smart battery management systems that just have fixed values, and those are great. I have those in a couple of my other packs as well, so that works out. And then this is the pack from the outside. I bought myself a little USB-C power box as well. So the one that's built in, I think only does, it's 30 watts or something. And then I bought this one, which does like 65 watts or 80 watts. So you can get different conversion boxes. This way I can run a laptop off it, off USB-C. Discharge curve, pretty similar again, very flat, 13 volts all the way out, and then drops off. But again, came in above design capacity. So that one came in at 52.5 amp hours versus the 50 amp hours that the cells were spec'd at. Question in the chat from James: electric lawnmowers have lithium iron phosphate batteries that deliver 40 to 80 volts. Can I safely connect those batteries to my radio equipment using a DC to DC converter? In theory, yes. Yeah. So as long as the output voltage or the voltage that you're providing into the radio is within the radio specifications, that's totally fine, right? So DC to DC converters for 48 to 80 volts going down to 13.8 volt, you can probably find them. It's a pretty big step down, so it might be a little bit more expensive, but because they need some bigger components in there, but that can definitely work out. There's also a question in the queue. Can't quite see all the hand there. George, you had a thing?
Yes, I have a question about your specific energy or energy density that's based on weight. Well, what about volume? Because my concern is use in laptops. I do not like the unwanted energy releases possible with that and other things. Why do they not want to use them, which would be safer?
Yeah, a great question, George. So the short answer is because consumers demand more, right? So when someone's buying a laptop, one of the key factors is runtime, right? And if a key factor is runtime, the two ways to get that is one, put in a higher energy density battery and get more battery capacity, and the second thing is to reduce the power usage of the device, right? So Apple, for example, building their custom chips, they can customize their chips to be as energy efficient as they possibly can, which is why things like MacBook Pros and the new Mac Airs and M1s and everything can be extremely power efficient and run for really long. I don't actually use a Mac myself. I'm on an HP laptop right now, but they, with less customization, they don't necessarily do that. Now, that being said, there are applications where people are putting lithium iron phosphate batteries in, for example, exactly that reason, because they are safer and they're less dangerous and less likely to do things. So you do actually see, like Tesla, for example, even for their Model 3, they have a variant of their Model 3 that is lithium iron phosphate based, right? And that is largely, so partially supply and demand, that there are raw material shortages for some of the other chemistries that drive up the costs, and partially also the safety concerns, right? There are factors that make it work out. So that's kind of food for thought there. Did I answer your question?
My question, one of the main parts of it was energy versus volume as opposed to energy versus weight.
Yeah, so the volumetric energy density, I don't have the numbers in front of me, but it's lower for lithium iron phosphate as well. So the specific energy versus volumetric energy density, or yeah, gravimetric versus volumetric energy density. You can look them up. YouTube has or not YouTube, Wikipedia, I think, has a good page with some summaries of that. I don't have the numbers handy, but short version is lithium iron phosphate for the same volume is going to be less energy than a lithium ion chemistry, right? And then when you push the limits, things like the Samsung Note fiasco, they're pushing the limits where they went with a very, very high specific energy. Both volumetric and gravimetric energy densities were very, very high, pushing kind of the limits. And then you run into issues because your design margins are much smaller. So short answer, hopefully, addresses that. Cool. So I'm almost finishing up here, last couple slides. So kind of comparison table. I don't really know, take this with a grain of salt, but I threw this together with kind of different color. So lead acids, they are cheap per amp hour in theory, but they are really low energy density. They're very heavy and they don't like low voltages. But they work pretty well for 12 volt DC, except you can only get half the capacity of the battery out of it, roughly, right? And again, kind of some asterisks on this. Lithium ion batteries, over voltage concerns, integration concerns, you need your buck converters, boost converters, but high energy density and pretty good pricing. Lithium iron phosphate, really, really good for 12 volt. You can hook up directly, so pretty straightforward to integrate, and honestly, a great, great solution. So um, my short version is you either buy one or build one, and I kind of talked about this briefly. So top right here, these are big batteries. So this is like shack backup. So 100 amp hour battery from SOK. They make some batteries that are pretty well recommended these days. So $500-600 for a 100 amp hour battery. That's 100 amp hour lithium, so it's equivalent to like a 200 amp hour lead acid battery. And if you look online for a 200 amp hour lead acid battery, it's probably around $400 or something. So you're marginally more expensive than lead acid, but this will last you way more, way longer, and way better. Similarly, if you want to build your own, you can buy the cells raw and then buy the battery management system. A couple links here. They're also on my QRZ. You can download this slide. So that's pretty helpful. And that pretty much covers the slides. So I'm going to switch over to Q&A mode and try to address anything else we have coming in through the questions. So I've got a couple.
I'm going to
Yeah,
interrupt
go
you
ahead.
for just a quick second.
Sure.
Jeff has put the drawing link on the chat. So if you're inclined to enter the drawing for the HRO certificate, we'll go into the chat, and it's about the third one up from the bottom right now, and go to the link and follow directions. Simple, and you don't have to, but if you want to, please go in and do that. So go ahead, Marcel.
Cool. Thanks, Jerry.
Question.
Go ahead, Frederick.
Okay, yeah. On a larger scale, I've always been curious. They're really pushing these electric cars. Just exactly what's the life of one of those batteries and the cost of replacement and maintenance? I know that's not amateur radio, but I might want to plug my radio into one at some time in the future.
Yeah, no, very, very relevant question. I think Gerald was asking a similar question in the chat too. So I'll briefly touch on electric vehicle batteries. I mean, high level, they're effectively like, this image too, you see there's a couple dozen cells here. Depending on how they're built, they're generally quite expensive, right? There's a lot of raw material going into one of those battery packs. Battery lifetime is always a question, and it's quite difficult to characterize because it again depends on how it's used and how it's abused. So a lot of automotive manufacturers will put something like a 10-year warranty on their battery pack to a certain capacity. So they've done their modeling, they've done their assessments, they've looked at the standard usage, like how fast people accelerate, how hot they get, how cold they get, depending on which environments they're selling them, right? They don't sell them in all domains. They don't sell Teslas to people living in Antarctica, and they don't sell Teslas to people in Saudi Arabia. Maybe they do, right? But you get the idea, right? It's different environmental conditions will change it, and change how long that battery pack's going to last. Now, with that modeling, they're going to say, hey, a 10-year warranty means that, if I'm putting on my product manager hat or my salesperson at Tesla hat, that means that we've calculated that, I don't know, 99% of people are going to have their battery stay above some percentage of total remaining capacity after 10 years of normal use, right? And 1% of users are going to have to use their warranty, which means it's going to cost us this much, right? So they do some math on that to put their warranty in place. And realistically, that's kind of how you can do your math. So there are two factors in the age here. So one is cycle life and how it's used, right? So increased cycle life, increased depth of discharge, increased operating temperatures, increased operating currents. All of those things will lead to accelerated degradation of the cell, so accelerated aging of the cell, where it'll not last as long. So things that you can do to increase the life of a battery, and this goes for all lithium chemistry types pretty much, including like cell phones and laptops, is don't charge them to 100% and don't discharge them to 0%. Keep them somewhere in the middle. Don't fast charge them, right? Every time you go and use a supercharger and do a direct DC charging on your car, you're eating away at the lifetime of that pack, right? You're pulling 1 or 2 cycles off the end of how many cycles that pack lasted. My cell phone, I think I've rapid charged it 2 or 3 times in my life, using like the 30-watt charger that it came with. The rest of the time, I'm slow charging it as much as I can. So my phone's at, I don't know, 2, 3 years old now, and it's still at like 85% or 90%, 87% capacity, I think last time I checked, right?
Okay.
So slow
Okay.
charging, don't charge full, don't leave it empty. Did I address all your points? You had one more question in there, I think.
Well, we got a little off there, but anyhow, we're not going to have to change the car's battery every 3 years, umpteen $1,000. But it's
Yeah,
always
you shouldn't, right? You shouldn't, unless they're manufacturing defects or if it's getting abused, right? So in industrial settings, they do plan that. Like industrial forklifts might actually plan to have their batteries, because they might be doing full cycles 3 or 4 times a day if they're getting used 24/7, right? In various shifts, they might plan to replace those batteries after 3 years because they're going to hit their cycle life.
okay.
Right?
Very good, thank you. And just always curious. They always selling the electric cars and never want to talk about the expense of maintenance. But anyhow, much appreciate and thank you so much for the presentation.
Yep. Yeah, sure thing. And one last point, I say a bunch of questions in the chat, but I'm really passionate about this whole circularity and second use and second life of batteries too. So there's a big push in the industry right now for electric vehicles to have the packs when they're no longer like meeting performance specs for customers. So they're not dead batteries, they're just not as good. They have lower range left on them. They don't accelerate. They can't, accelerate their car as fast. Those packs can now be used in second life applications. So things like even today, Nissan Leaf batteries are being used for off-grid solar applications, used Nissan Leaf batteries. Rivian, the new truck manufacturer, their packs are designed to go into grid storage applications after the customer's done using them. So after 5 or 10 years, if the customer needs to replace their pack, the old pack can get sold to a third party that then builds grid storage, right? So those are, I think, really cool applications. Okay, let me get a couple questions in the chat, otherwise we're going to fall behind. James asked, BioNO cautions against putting their packs in parallel. Is there a safe way to do that yourself? Yeah, so this really depends, and you have to go by the manufacturer. So depending on how the battery management system is built and designed, some are designed for parallel use, and that's okay, and some are designed for series use, and that's okay, and the other is usually not okay. It's rare to find one that can do both. So you have to be a little bit careful in how that's done, and that has to do with how it's designed. BioNO typically cautions about that in parallel, because if you're, depending on how you're hooking them up, you don't want the current to suddenly flow from one to the other. If they're full-time hooked up to each other, it's not an issue. But the problem is, since the packs protect themselves, if one of them protects itself for an overcurrent event, for example, that pack is now open circuited its protection circuit inside, and it's now sitting at that voltage, whatever voltage it was at, but it's not connected to the bus that the other pack is on. That other pack will now start discharging, and at some point, that condition is going to clear. It's going to close that circuit again, and now it's going to attach this higher voltage battery to the lower voltage battery because they're in parallel, and now you have this mismatch, and there's going to be effectively a short circuit, a high current flow between those two batteries when that happens. So that's the main reason why they caution against it. The way to do it safely is kind of complicated, and actually industry struggles with this as well, because you're adding a whole bunch of circuitry to connect or disconnect or carefully connect or slowly connect and like bring the voltage up slowly and current limit it. You effectively need active current limiting devices in parallel to make sure that you don't then have these like rattle conditions where it rattles back and forth between connected and disconnected. So hopefully that addressed your question. Gerald, I think we covered most of the Tesla issues. How do they solve issues with overheating and fire potential? So overheating on the batteries themselves. So a lot of electric vehicle packs, especially for high performance vehicles, have full-blown cooling systems in them. So like the Tesla battery packs have glycol lines running through the packs like tubes, and they're literally running fluid around the cells and through its own radiator to cool the packs.
NBC
and that kind of aligns with it. For fire potential, there are a whole bunch of things you can do in the design. Again, it's trade-offs here, right? If you space the cells, if you're using individual cells, spacing them further apart, so like 2, 3, 4 millimeters between the cells gives you less potential for the pack to have propagation fires where the fire moves from one cell to the next, but it makes the pack that many millimeters bigger in all directions, right? And so there's, again, a trade-off there with the consumer of how much range do you want to get into this battery with how much energy density can you pack in there. So inherently, the more energy you squeeze into a small space, the more dangerous it is, right? Start with fireworks, think about grenades, go to C4, and then go to nuclear, right? You can kind of get an idea of there's higher energy density as you get smaller there, and it gets more dangerous. Did I answer your question, Gerald? Cool. Jeff, are you aware of any consumer UPSs that use LFP instead of SLA? I've been asking the same question myself. Off the shelf, there are a few. They're very expensive for the ones I've found because they're kind of a niche market still. You can, for a lot of those consumer UPSs, you can just buy drop-in LFP replacements that fit those, and those will usually work. But again, it's a little bit goofy with voltages and how the charging and float charging works for the UPSs. So, I mean, read carefully and do some tests to know what you're doing. You will void warranties, of course, obviously in that case. But there are a couple rack-mounted UPSs that use lithium iron phosphate batteries or lithium batteries. Those are more common, I think. But consumer ones is kind of difficult to find. Jim asks, if my radio requires 13.8, then the LFP is rated for 12. Will I always need to run it with a boost converter? No, not necessarily. So again, 12 volt is a very loosely used term. So even lithium iron phosphate batteries are labeled as 12 volt batteries, but really they're not 12 volt, right? I think going back to that slide here, right? Your nominal pack is between 10 and 14.6, right? Because it's really 3.2 times 4, which is 12.4 volts, right? Yes, technically that's lower than 13.8, but those radios are operated 13.8 plus or minus 15%. So as long as you're in that range, that's typically what they do. And actually, I have that on a slide too. Whoops, that blew us out. Sorry. Oh, wow, that was impressive. We lost everything for a minute. Okay, am I back?
Yes, you're back.
Okay, I was going to my last slide, which then exited out. But give me just a minute and I'll reshare that. To be careful not to go past that, apparently. But, here we go. Go back to share. Apologies there. This one. Okay, so this is just pulled from a bunch of the data sheets. Can you see that now? Yeah, hopefully.
Yes.
Okay, cool. Oh no, and I lost the chats. Okay, if someone can repost the chats from where we were, that'd be super helpful for the questions. Or repost your question if it hasn't been answered yet. So yeah, this shows you different mobile radios for their voltage specs, right? And it's kind of interesting because not all of them give you, most of them again here are 13.8 plus or minus 15%. And then some like the FT920 is 13.5 volts plus or minus 10%. Who knows why, but apparently that design specifically required that variance. So that one you have to be a little bit more careful because it's a little bit narrower. And then some of them like the FTM10R doesn't say plus or minus 15%, but it gives it the same voltage range. So it's actually the same equivalent there. So yeah, I think that answered the question. And yeah, apologies, I apparently lost the chat. So if you want to repost your questions or if you want to ask them verbally, if I didn't get to that yet, then go ahead. Anyone? Or if someone wants to ask the questions that I hadn't answered yet that were in the chat.
How many of them did you get? Let's see.
Cool. Yeah, I don't.
I'm not sure if you.
We dropped off it. Yeah, that was the one I answered, the Jim Blanchard one. So the 13.8 LFP for 12 volts. So the ones after that, if someone could drop those in the chat, that'd be helpful, or read them out loud. That's fine too.
There was one that said not cheap, but maybe simple. I noted a company called XS Power makes a 14-volt automotive AGM battery, maybe a deep cycle version available.
Yeah, and that's in the lead acid space. So again, those are typically going to have lower shelf lives, and you're going to have limited capacity, and they're going to be heavy, right? So quite honestly, today in amateur radio, I really cannot recommend lithium or lead acid for most people. There are a couple specific applications where it'll still make sense, but for most people, especially if you're starting with a fresh system, start with lithium iron phosphate. That's really the way to go. That's the chemistry of choice. Other questions?
I don't have a question. I just wanted to say I thought it was a great presentation, and thanks for giving it to us, Marcel. You see so many things on YouTube and on QRZ where hams are building these LFP packs and going and doing great stuff portable with it. And it's really cool to have that information here in a sort of compact presentation. It's a great starting point, I think, for anyone who's trying to do that. So thanks.
Yeah, thanks, Alex. Yeah, it's always a challenge to figure out what to talk about, but I like providing that background and kind of walking you through the understanding the why, because I think that's really important for amateur radio. I don't want us to become appliance operators, right? And I argue that someone building a battery pack following a YouTube video is pretty much an appliance operator, because they're buying almost a kit online and just assembling the pieces. They don't actually understand what they're putting in, or why they're assembling it, or why they need that battery management system. So I think it's really important to understand the why behind it, so that you can be smarter about the decisions you're making and be more careful with how you're doing that.
Makes
Question.
sense.
Yeah, thanks, Alex. One question from Gerald as well. Discuss the future of solar power and the future of battery technology. Yeah, so solar, well, let's do a brief 30-second version, maybe. Could go on for an hour on this. I have a whole separate talk on solar too for off-grid systems, but solar technology briefly, I mean, the prices keep coming down largely through subsidies. There's a lot of surplus solar on the market. So especially, again, with respect to amateur, I'm going to try to avoid going too broad into the greater world. But if you can find a local surplus seller of solar panels, if you're looking for solar panels for your project, that's a great way to do it. Typically, when they install a large system somewhere, they'll have 5-10% extra panels just in case of breakage or mismatch or something. They then sell those dirt cheap after that project's done. So you can get cells for half the price, get big solar panels. That's huge. So I've gotten a couple of panels that way. I know my university actually, they got something like 20 pallets of panels off a huge project that was a large grid connected solar project, and the excess panels, that company donated to the university, and it's been great because they've been doing tons of projects with it, and they've given some of those to the local ham community as well. So that's really cool. Future battery technology. My short joke is, every couple months you'll get some article for some research paper, I should say, published from some small university group somewhere, that gets picked up by a news outlet that says this is the next greatest battery technology. It beats all these specs in all these ways. It's 10 times the energy density, charges 10 times as fast, lasts 10 times as long, et cetera, et cetera. And it's not the case, right? I mean, yes, in one small sample in this corner condition in a laboratory environment, yes, they can meet those conditions and it'll make it. It makes a great BuzzFeed headline. But until that is mass market and manufacturable and has proven technology and has a proven supply chain, it's not going to be something that hits the mainstream, right? So again, looking back at lithium ion batteries, 1970s, lithium iron phosphate, 1996, really it was only in the last, I would say, like 5-ish years that they really started exploding, is the wrong term to use in the battery world, but really getting broad in the community, in the usage in the industry, right? Lithium iron phosphate batteries were kind of a niche thing that was used for a long time. Now, like in the last 5 years, they're everywhere. In the last 2 years, you can get them literally everywhere, right? And that's crazy, right? So that technology, even though it was invented like 1996 is when they put out that research paper, it took that 25 years before it really took off. Right. So I put that same caution is, yes, those technologies are going to get worked on. They're always going to exist. And that research and fundamental research is critical and important to push us to the next generation of electrochemical energy storage. And that's really what I'm going to put batteries in. right? And electrochemical energy storage will continue to develop, and people will keep finding things, but finding that next breakthrough technology that is actually widely used everywhere is going to take time, and it needs to mature, right? So lithium-ion batteries as well, early 2000s is probably when they kind of got big, and that was 20, 30 years after it was developed as well, right? So that's my short theory there, Gerald.
Hey,
Yeah.
Marcel,
Yeah.
with automotive, the Teslas, the whatever car you want to talk about, they've got hundreds of cells, correct? I mean,
Thousands sometimes, yeah.
thousands of cells. So you got a projection this pack should last 10 years. So what, it's hard for me to believe that, you know, um, one or more of those cells at some point in time is going to go bad. Are they made some way where it takes that cell out of the circuit, or what? What do they do? In short,
Yeah, great question, Jerry. So in short, yes, that's a key design factor actually, especially when you have that many cells. The probability that one of them is going to have an issue or degrade faster than the others is quite high, and that's one of the things that can happen. So depending on the system design, can't speak to the specifics of those battery packs from like Tesla's or Nissan Leafs or other automotive manufacturers, but some of the packs, like my friend builds some pretty big power walls himself, and what they'll do is they'll put individual fuses on every cell. So every single cell that's in parallel, because these will be large, again, series and parallel combinations of packs, might be, I don't know, 100S and 100P, like quite literally in some of these battery packs, like that sort of size. 100 cells in parallel, if one of them fails short, suddenly 99 cells are putting their current into that one short pack, right? So if you just hook them all together in parallel, that one cell, when it fails short, will explode, right? Because that's a lot of current going to that one pack. So if you fuse that individual cell, it will briefly go over current until that fuse pops, and then suddenly that string will just have 99 cells in it, right? All the other strings will still have 100 cells in it, and that one string will have 99 cells. So then what happens is when you charge and discharge that pack, if you charge, when you charge full, that 99 string is going to actually get to 100% faster. So it's going to hit over voltage faster. And then when you discharge, it's going to get to under voltage faster as well. So it's going to effectively decrease the total capacity of the pack kind of by that one cell. But you could see that happening. And if that one string loses another, then it's down to 98, then the whole pack kind of goes down to 98 cells worth of capacity. Now, if the other strings in parallel also start losing one cell here, you could actually keep going for quite a while before the pack is like significantly degraded, unless they all happen to be in one of those strings. But probability wise, that can work out. And that's kind of one of the mental models around designing packs for long-term usage. So in electric vehicles, you might only use them till they're at 80 or 70% of their design capacity before they kind of don't work great for high charge and discharge because their resistance increased over time, and their capacity has gone down. But if you have 100 or 1,000 of these used electric vehicle battery packs in a large grid setup, like on like energy storage system attached to the grid, the power grid, it doesn't really matter if those packs only have half their capacity. When you have 1,000 of them, you just have the equivalent of 500 new battery packs, right? And you don't need to charge and discharge them at these really high rates. You're not supercharging them on a Tesla charging station. You're just providing grid power here and there, right? And you're smoothing out the grid. So for those applications, it can be super, super useful. And if you set up those systems out in the middle of the desert, then if one of those cabinets catches fire and it does have a catastrophic event, it's not the end of the world. It's not going to cause an issue, right? It's not going to burn someone's house down if it's designed correctly. So,
well,
yeah,
thank you for that. I think we'll break here and do our drawing. So if
sounds good.
anybody wants to cut out, and Jeff will, we have it so it electronically picks, and then if you want to hang on, if we got other questions, if you want to dive deep into something,
Yeah, can do.
we'll do that. So Jeff, whenever you're ready, I think we've had plenty of time for anybody to get in that
And
wants
we've been
to.
holding 17 responses for a while, so I'll go ahead and
Okay, pull the trigger.
randomize it here. Looks like our winner this week is Evans Moak. Hope I didn't destroy your last name. KF0FPI.
KF0FPI. Evan, you said it is?
Evans, EVANS, H
Okay,
Moak, MOAK.
What's the call again?
KF0FPI.
F0.
With Ron also.
You kind of, thank you, Kevin. You kind of destroyed the last name. It's Moke. Just take an oak tree with an M on it.
Okay.
And it's Evans Moke, and my nickname is Ron. I try to go by Ron when I call in on Wednesdays.
Okay. Well, congratulations. Kathy will get the certificate out to you, and thanks everybody for participating.
Appreciate it.
We will. I'm sorry.
I appreciate it.
Okay. Thank you. You're sure welcome. So I'll go back to mute and go ahead and continue. Marcel, anybody wants to? We thank you all for joining and listening. So you're welcome to hang out or not. And Marcel, back to you.
Sounds good. Whatever you'd like to pick my brain on. Not all at once. Feel free to jump.
Well, maybe we've ran out here. I don't know.
I have one question for you, Marcel. This is Jim.
Yeah. Hello, Jim. Go ahead.
I asked the question about putting those bio-NO packs in parallel, and I like your explanation for it. If I can't do that and I can't afford to buy a bigger bio-NO pack that automatically takes care of that for me, is the best strategy then just when the first battery gets depleted, disconnect it and hook up the second battery in its place?
Yeah, that would be the best option. The other one is if you can do a, I think this one would work. I'd have to go double check, but PowerWorks sells, or maybe West Mountain Radio sells it. There's an auxiliary battery unit for a car, and it's specifically designed to have your car's starter battery in the engine compartment and a second 12-volt battery in like the bed of your pickup truck or under a seat or something that's separate and disconnected, but when it connects them, it current limits between the two. So you could get a device like that. Honestly, if you find something, the BioNo folks are great at answering emails and technical emails. So if you kind of put together a suggestion, or feel free to bounce it off me too if you want to discuss technically a little bit. I'm happy to throw those ideas together. That we can look at what that option would look like for making that work properly.
Thanks, I appreciate it.
Yeah. Other questions?
Anybody?
Can do my brief plug on phone batteries. I should add a slide deck on this, but there's an app called AccuBattery, which you can install on your phone. If your phone's not rooted, it'll just give you a notification, but you can set notifications to set an alarm, for example, at 70 or 80% when it's charging. There is also a device called a Chargy that a gentleman over in Eastern Europe makes, and I have several of those now, and absolutely love it. It's a little Bluetooth controlled USB device. I think mine's in the car right now. I use it in the car as well for longer drives, and it plugs in series with your USB cable to your phone. And then there's an app that runs on your phone, and when your phone hits a certain charge level, it turns off the circuit, right? So the little Chargy that's plugged in will open circuit. That's a awesome way for super battery nerds to really play the battery game, where we can control the charge levels in our phone and really get control. A lot of manufacturers don't give the consumer control over it. Apple does have a built-in system, and Google and Android has one, has a very basic one as well that you can enable, where it like learns your routine and then only fully charges the phone right before you're about to wake up or your alarm set in the morning, for example, if you leave it plugged in overnight. But otherwise, if you leave your phone plugged in overnight, especially on a fast charger, you're doing the worst of the worst. It's fast charging it, which heats up the battery and degrades it faster. And then it's sitting at 100% from, I don't know, you went to bed at 10 p.m. and then it stays at 100% until you wake up at 7 a.m., let's say, right? That battery is now sitting at 100% for the whole night, and it started hot, which is just aging it really quickly. So that actually causes a lot of damage internally to the battery, which is ironic because that's kind of how they sell devices to us, right? So my phone's hooked up to this Chargy, so at night when I go to bed, I can plug it in at whatever level. It's a slow charger, so it's only a 5-watt charger, and it's going through this Chargy device, and it charges slowly to 5 watts up to 80%. And then it'll discharge to 70, and then it'll charge back up to 80, and it'll discharge to 70 and back up to 80 overnight. and I think it does it like that maybe once or twice in the evening, depending on how much is running on the phone. But that's a way that you can kind of control and maximize the life. So again, to the point of trying to prevent waste from my perspective, that's my little way of there's no reason to replace the phone after a number of years. Typically, they just don't run as long, so they might only last for half a day now, and then you're always constantly tethered to a charger, and that can be frustrating. But you do have to trade off because if you're only charging up to 80%, you're also losing that upper 20% of capacity. So uh, your mileage may vary. But that's my short blurb on cell phones and laptops. Same thing. If your laptop has a way to, if you're using a laptop at a desk 95% of the time, see if your laptop has a setting to not charge your battery full. Like there's sometimes at a docked mode. A lot of newer laptops have support to only charge to 70 or 80%. That'll make your laptop battery last way longer from a year's perspective, right? It'll last years instead of sitting at 100% hot on the dock, not breathing, not having a fan on it, and that'll degrade them very quickly.
So I would gather you're not a proponent of wireless charging for phones?
I don't wireless charge on my phone usually for all of those reasons, because wireless charging adds heat and it adds and I mean they're typically selling it as fast charging as well. I do have a wireless charger though, ironically, because my phone has the little metal plate on the back because I use the magnetic mount, that blocks any regular Qi charging. So from that perspective, I'm kind of prevented. When I do use it, I have to take the case off, which kind of defeats the purpose. But wireless chargers are good. You're not cycling the USB port. So then the USB port lasts longer, but your battery might not last as long because there's going to be more heat generated from the wireless charging circuitry. I'm definitely not wireless fast charging. Not a fan of that from a battery chemistry perspective, right? From a technology perspective, fascinating. Absolutely love this stuff. And I'm an electrical engineer still, right? So don't forget that. Cool. Other questions?
Hey, Marcel, I asked you earlier about, temperatures and bioenno batteries and stuff like that. And I think I'm getting the high sign to pay attention to other things. So what I think I'm going to do is I got to sign off, but I'll send you an email and kind of describe what we're trying to do and if you can offer any advice.
Sounds good. Yeah, the short version would be the lithium batteries that have built-in heaters would probably be your best bet, because those will handle it. They just take more power, so then you have to account for that in your power budget. So that's
The
always a
problem
challenge.
is the heaters may create magnetic fields, which we want to stay away from.
Oh, that's exciting. I want to hear more.
Yeah.
Sounds
Okay.
good. Okay. Cheers, Bill. Thanks for joining. Yep. So that makes me think that he's working on one of those projects for like USGS where they're measuring the Earth's magnetic or the mantle under the Earth's crust and detecting the depth of the mantle. I had a friend that was working on projects like that, so pretty fun stuff.
Well, if there's no more questions, we'll cut you loose, but sure appreciate it. Any finals from anybody out there? Apparently not. So we sure thank you for taking the time to do this, and I'm sure Bill Rinker, schedules our stuff, and if you've got other related things, I'm sure we'd love to, get another time with you. And you're a
Yeah,
very
sounds
good
good.
presenter and very interesting. So thank
Thank you,
you
Jerry.
very
Yeah,
much.
thanks so much for having me. It's always fun. Actually, be in the Denver area over Christmas. It'll be fun. I'll be right in your neck of the woods.
Well, get on one of our
Maybe hop on the
repeaters.
repeaters. Yeah, that's what I was thinking. It'd be kind
Yeah,
of fun when I
look,
drive through.
w0tx.org.
Sounds good.
On our
Yeah,
website, they'll be there.
sounds good. You'll have to try to fit that in. But yeah, no, it's good fun. My talks are on my QRZ page, so that's probably the best way to see what you might be interested in. That's my
Okay.
current list of talks, and I'm always have new ones in the works. But I usually do
Okay.
one or two new talks a year.
I'm sure we got your, I got your QRH, your
Yeah.
page here. So great.
Cool.
Well, thank you.
Yeah, thanks very much, everyone. Have a great evening.
Everybody for checking in. Good night.
Good night.
NBC Television.